All right, welcome back. So I hope you had a good week and you had time to study the material in detail. So we will continue our journey into regression and into applied biostatistics 1 today. And now we're really digging deeper into regression analyses. So I hope everything has been good so far and the BAP wasn't a big issue. You're getting a handle on data camp and this is all moving forward. I hope these technical glitches were resolved. The discussion board is, I think it's a good forum to have these conversations and to kind of troubleshoot whatever may have gone wrong. But let's continue the conversation. So I really try to be observant of the discussion board. So please post all your questions to the discussion board. And this includes not only technical questions or questions concerning the course, also our questions and also questions concerning the material that we're discussing. Okay, so let's continue. So I hope you had a good week and you are ready for some more regression. Okay, so today we're gonna continue our conversation about simple linear regression. We will be talking about the differences between regression analyses and correlational analyses and the pros and cons of that. We will talk about notations. So there are some very peculiar kind of ways how notations are presented to you in regression analyses. And in this context, it's also important to understand what the components of regression analysis are, what they mean, and what they imply. This includes particularly intercept and slope. And you will very soon see what is meant by that. And we have talked about the intercept and slope in very broad strokes. And today we're going to dig a little deeper into what intercept and slopes and the other components actually mean. So we will also talk about the interpretation of regression analysis, and we will talking about the centralization of predictors. And this is quite central, and you will see why this is important, particularly in the context of physiological or pathophysiological kind of analysis. And yeah, and then lab 2 will be a separate video. So I'm always splitting it up to kind of be able to focus really on one topic per video, and to also give you a chance to have this a little bit in a more digestible form. So I think that makes a lot of sense. Okay, so linear regression was one covariate. So in a two-sample t-test, essentially you have you have a binary variable. So you have a grouping that is a 0 and a 1, and you're comparing the means between both of these groups. In essence, and we have discussed that the last time, where you essentially include a term that stands for this grouping as a binary variable. So you're adding to the mean that estimate for that group difference. So you're adding the difference. So when you take now a continuous measure for an individual I, so blood sugar level here coded by Professor Sang as SL, you will basically try to predict YI for that individual at a known blood sugar level. So you're essentially meaning to predict systolic blood pressure at a known blood sugar level. So this model 1 essentially is conventionally called a simple linear regression. For confounding-based modeling, such analyses are called univariate analysis. Univariate analysis essentially because it only contains one variable, right? So it's essentially the same thing. It's kind of a synonymously used nomenclature, but it's important to basically distinguish a univariate analysis to a multivariate analysis that we also will be discussing later on. Because with multivariate analysis, it's not only one confounder that plays a role. So you will want to add additional confounders to your model, and this will basically render your linear regression from the status of a univariate analysis to the status of a multivariate analysis. Good. So there are different ways to write such a simple linear regression model. And the mathematical way essentially is shown here on top, where you basically see the yi, which is your left-hand side. And we have to discuss the point. So this is basically a repetition of what we discussed in last class. So we have our yi, we have our intercept with the beta 0. We have the slope of beta 1 of that predictor of every individual xi. And we have a residual error, which essentially is normally distributed around a mean of 0 with a variance that is basically reflected around the predicting, about the predicted model, the predicted estimates based on that model. Another way to, what is the IID referring to? So the IID essentially refers here to each individual in the group, and essentially is something we will be discussing later on. So another way to depict this is essentially by y equals a plus b multiplied by x, which again corresponds here with the mathematical outline, plus the residual error. With a particular error in SPB equals a plus b, which is the slope, multiplied by the SL plus e. It's the same thing. In R, you would basically write it as fit, and we have done this in last class, LM SPB as a function of, so the tilde indicates as a function of 1, indicating that intercept plus SL. So you basically mean to kind of use a depiction format that's corresponding with the mathematical format. So we are trying now to test this alternative hypothesis. So is blood pressure related to blood sugar level? So usually you would always phrase your hypothesis in a way that there is an underlying physiological hypothesis. So we know to some extent that blood sugar level does associate with SPB. It's not a very strict relationship, but there is a relationship. We know that. We also know that diabetics more likely are going to have atherosclerotic vessels. As a consequence of that, they're more likely to have elevated pulse pressures and blood pressures. That is usually not a good thing, and which will then in the longer term lead to a deterioration of the oxygen perfusion in organs, particularly the heart. So this is essentially the reason. So this atherosclerotic process is essentially the reason why their oxygenation of the myocardial muscle is not functioning that well, and they are prone to have cardiovascular disease and also have consequential cardiac problems. So at this point, then it actually can be that this association that we're seeing right now, this positive association that we're hypothesizing at this point, is essentially becoming inexistent because their cardiac function has decreased and they actually are not able to keep that blood pressure up. So from that very reason, this is probably a subset of patients we should be looking at where we see this association. And this is where confounders and biases come into play, because at patients that have had diabetes over a long or protracted period of time, that association would not be present. So this is how you have to think about confounders, right? So this is where things actually really then coming into play and interacting with each other and interacting in a way that you will need additional information fed into your model to account for that and still have a stable and accurate estimate of what you want to predict, which is here SPB as a function of blood sugar level. And this is the way you have to think about this. This is the way how you have to approach epidemiologic studies. Okay, good. But let's do this now quickly, and let's have a look what Professor Zhang has coded here. So again, so you will have in your weekly folder. So I'm having it here in week 2. So I really encourage you, create a BIOS620 folder, have week 1 in one folder, week 2 in another folder, have lab and lecture separated, because your lab, you will get 4 files from me for the lab. So this becomes a lot of files. So like keeping overview is probably what you really should be prioritizing. So we have here 2 files. 2 files I will post, or I have posted, which is 2 PNG files, which are needed by the RMD, the Markdown file. So if you open the Markdown file, I have it. So you can basically run this PDF, but make sure that the 2 PNG files are in the same folder. Otherwise, you're gonna get a hiccup, and you will not be able to get over that hiccup. Okay. But now let's see what we have here. Okay, so we have now, okay, this is on line 68. You're actually seeing what we are doing here in the PDF. So if we, and I want to emphasize 2 things. So if you work in Markdown, you're essentially looking at 2 things. So you have here the console. You have here the script, the Markdown script. You have, again, you have here the environment. You have here the outputs, the help, the views, the packages, blah, blah, blah. Here you have the console. So on the left lower quadrant, you have the console. You have the console, the terminal, which you won't need. Then you have Markdown. This is where Markdown runs down the whole thing and generates PDF. And these are the jobs that are currently pending, which the jobs you're doing here for this class are so marginal, you will never even see this happening. If you, for example, if you run big data in R, you will see a lot of jobs there. So all these jobs that are currently pending, and then it is actually pretty good to have an overview and have an idea what jobs are actually currently in the workload. Okay, so looking at the console, we can now run these 5 lines, just like every other R code. But you gotta be in the console, not in Markdown. In Markdown, it would give you a hiccup. Okay, so now we have this generated. Just for you to understand, rnorm and rbinom are essentially functions, how you can randomly generate data. And this is beautiful, because essentially this is giving you random data, simulated data, that essentially represents the shape and form of a real data set. This is the histogram of age. And it's also quite well chosen with, so you're choosing here 100 participants with a mean of 35 with standard deviation of 5. And it's actually pretty good, because likely we talked about diabetics, we talked about the association of diabetics. So it's actually kind of realistic in a way, because here you really may see this association, this positive association between blood pressure and SPP, blood pressure and blood glucose. Whereas in older individuals, that would not be here, and would be an unrealistic simulation. Okay, so now we have this. This is the most common hypothesis in epidemiological studies. So we're basically trying to relate one variable with another variable. Good. So now we're trying to do a scatter plot. Now that's easy, right? So we know that already. So we're running the fit. We do have a loose association, which we know. We can do summary fit, and we get a summary of that fit. There's a remarkable delay. Okay, so there is an association. So this simulated data actually builds a simulation, builds an association. And now we actually, so that builds now a data frame, which is the length of SL. So 1 to length of SL. This is actually 1 to length of SL. We know that SL is 100. So sequence 1 to SL will give us like 1, 2, 3, 4, 5. So let's give it a sequence of numbers up until the maximum of length of SL, which is 100. that we have SL, which is our simulated parameter, and SPP. And we are basically now building this data set, and this is essentially what we're seeing here, right? So this is essentially the data that Professor Sang has shown us. Note that these are different values, but are not different. And now we can also plot this data, just like it did here. So really, I encourage you to go into the Markdown file and look at the data and have a comparison of the data. So, and this is now where we're essentially going. So you all remember that there is a correlation analysis, right? And there's definitely a possibility to do correlation analysis. So correlation analysis gives you the so-called R. And there is an association between simple linear regression and the correlation coefficient, because you get via standardized coefficients, you actually get to your estimates. However, these are calculations that are quite something that you may or may not already have done in your previous studies. At this point, we don't really need to revisit this. But we could. Actually, we can do this in the lab. Let's do this in the lab. Actually, it's an interesting analysis to do. It's an interesting exercise to do. We can actually, I'm not do it right now. So I have here, this is from, just a second. So if we are essentially calculating based on, so this is essentially how this presents itself when you're doing this live. So you have an association between, sorry about that. So now I wanted to show you something and I will find it. That was funny. Okay. Second. Just a second. Just trying to find the right file, which is kind of, oh yeah, there we go. Okay. So this is a calculation I used to show my undergrad. But I show you this for you to get a grasp of what the association essentially is. So if you are using a Pearson correlation coefficient, you essentially are testing the hypothesis that your correlation coefficient is different or significantly different from 0. Whereas an R of 0 is essentially a flat line or a vertical line, both of which essentially are coming to the same end, right? So what your R is reflecting is a significant increase with the increase of one variable of a fitted line. And it does that by essentially building a sum of the products of xi, so each individual data point minus x bar multiplied by xi minus x bar. So how does that look like? So this is the example I showed to my my undergrads. So we have here 10 individuals that have a certain number of stressful life events, so ranging from 1 to 5. They are essentially looking at, and this is what these stressful life events, x-axis, mean to predict, y-axis, right? So it means to predict that your depression is essentially getting worse when you have more stressful life events. Sounds reasonable, right? Obviously, the confound is again, what is the severity of a stressful life event? So if your girlfriend breaks up with you, no matter how, a boyfriend or whatever partner, is a dramatic, terribly traumatic event. It's like even so in the world of psychology, is like this can go as far as that people have PTSD. They have a post-traumatic stress disorder because of that, particularly when it comes to the really most terrible ways of having to encounter that you've been betrayed. It's like people really they are absolutely devastated for very good reasons. So there's a very reasonable kind of hypothesis in there. So what is happening now? So so now we have stressful life events, and we have the BDI reflecting depression, right? So now we have here mean, which is here 1.9, so 1.9 stressful life events, which again is debatable because it's a count, and the count of means that comes in both sets. But again, it's a simple example, just outlining that. So essentially what we're doing now is, so we have now y, and y essentially is our BDI. Again, we have a mean and we have a standard deviation. Good. So now we're building this x minus mx, x minus that mean, is now nothing else but this minus this. Good. So we do this 10 times for each individual. Now we're doing the same story for y minus my. And again, we get 10 differences. So now we're summing this up. This is the sum, right? From I equals 1, that's individual number 1, to I equals n, which is 10. So now we're summing this up. We're getting now the sum of squares, not the sum of squares, we get the individual squares, and now here we get the sum of squares. So that's the sum of squares. We get the sum of squares of x, we get the sum of squares of y. So what is this essentially meaning? So now we essentially, we are summing up our entire difference, which is 80.7, and we're dividing by the square root of the sum of squares. So we essentially, we're relating the sum of the differences to the sum of squares, to the square root of the sum of squares. So essentially, you're relating the differences from the mean to the product. No, you're relating the sum of the product of your individual differences to the square root of the sum of the squared product between these individual data points. As a consequence, you get now your R. What does that mean? In simple linear regression, and this is also a good point to make. In simple linear regression, your R square is actually the square of R. Don't let yourself fool you, because in multiple regression, this is not the case. So this is only true in simple univariate linear regression. So what you're trying to do now, so now you essentially have your R. Now you're trying to standardize your data. You remember from your introduction to biostats, you remember that you have, based on your mean and your standard deviation, you can standardize your X, right? So you essentially, your mean is 1.9. That's your zero. So you basically, you have your zero is, and this is now where I'm going back to your early way of introductory statistics. So if you have a set of zero, your set of zero is the mean. If you're going now one standard deviation to the right, this is now your mean plus one standard deviation. So you essentially, you're trying to standardize your normal distribution, right? If you remember the normal distribution, you have in the mean, and you have the mean in the middle and the center, building the center of your bell curve. And with each standard deviation to the right and to the left, you're capturing more and more of your data. So essentially what you mean to do here is that the calculation of your set X is essentially here. So if you go for 3 sets, so the set equals 3, you do 3 minus B14. B14 is your mean divided by your standard deviation. By that, you get that X value at which the set score is 3. So this is just rearranging the formula for the calculation of the set score. The same happens if you do it with 1. So you're getting H22, which is now your 1, minus B14, which is your mean. So you take the set equals 1 minus the mean, and you divide it by your B15, by your standard deviation. By that, you're getting the inverse. You're getting your actual X back. So by calculating this set, you essentially can now multiply. If you want to standardize that X, so this is 0, and so this is an X of 0, 1, and 3. So this is basically taking that corresponding set, and you have standardized now the entry of 0, 1, and 3 for your set. So if you want to calculate now based, and this is a correlation that that is an association. That goes very far back. So essentially, you can estimate your set y hat based on correlation and based on this correlation coefficient by multiplying your set X at 0 with your set with your R. Gives you a set y hat, a corresponding set y hat. If you do the same with set X and set and the R for 1, you basically get a set 1 hat for 1, for an X of 1. And now you can basically already think about what that means, because when you have a set y hat at X equals 0, this is your definition of intercept, right? You remember from first class? This is your definition of intercept. So if you are now using your y, because you know the mean of y based on your underlying data. So if you take K23, which is here your set y hat, multiplied by C15, which is the standard deviation, and you add the mean, you're going back to quantifying your predicted y hat, which is at an x of 0, which is your intercept. This gets you the intercept of your regression model, simple linear regression. So essentially you have that already booked. So you know your intercept. And now you do the same thing. Again, you do K22, which is your set y hat, which you calculate from your set x from an x equals 1. You get K22 multiplied by C15, which is your standard deviation, plus C14, which is your mean. And that essentially gets you to your y hat at 1. So this is your predicted y at an x of 1. And the difference between those two, that's your slope. Because the slope by definition, and we will talk about this in a second, and I mentioned it the other day, your slope is essentially nothing else but the increase or the decrease of y with an increase of 1x, 1 unit of x. Good. So I will post this. I will post this as a simple estimation spreadsheet as well, that you can kind of play around with it. But this is how you do linear regression. So this is the underlying kind of story with this R here. And this is great because understanding that will allow you to essentially also understand what we're actually looking at here with regression. So we have here yi. This is a your intercept, and we have calculated the intercept, right? So we have a beta 1, that's the slope, multiplied by xi. And this is the increase of 1x, of one actual x, not the set x, but the actual x. And you're using this increase to transform it in a set x. From the set x, multiplying it with the r gets you to the set y hat. From the set y hat, knowing the mean and the standard deviation of your underlying data allows you to quantify the y hat. And by that, you essentially, you have to build, you're already right there. And now you have, in addition to that, now you have to deal with this residual error. And this residual error, this will be something we're going to discuss down the road. But this is, this is basically, it's the variance around your estimate. It's the variance around the estimate that is kind of showing the precision around the estimate. Okay, so we have SPB equals A plus B. Okay, we talked about that. Left-hand side outcome, right-hand side covariates. When there are 1 plus covariates, yes, we talked about that. Okay, so now shifting from the correlation to the linear regression reflects a thinking to treat X and Y differently, because we have done correlation here with this equation. Right? It's like you basically do the sum of the product of the deviations. You add up the sum of squares and you divide it by the square root of the sum of squares for X and Y. This is your R. So now what's fundamental to this approach is that you treat both X and Y equally. And that's obviously not what's happening, because we are trying to predict blood pressure as a function of the glucose. So now we are essentially not doing what the correlation coefficient would be doing. We are essentially now rearranging our way of thinking. So we assume now that Y is actually an outcome and is causally associated with our predictors, which means this Y is a random variable, which is measured and found to present with an error or a variability within its accuracy. So now, on the other hand, the X as the covariate is now meant to be measured without a measurement error, and is perfectly measured. So this is not only a bad thing, this is actually absolutely never true. There's absolutely nothing that is perfectly measured, and I tell you that was 100% being convinced about that. Nothing is perfect. Nothing is measured perfectly, particularly not in the medical world. It's just impossible. Everything comes with the so-called coefficient of variation, because there's always some form of variability in the accuracy of your estimate. It's like every lab measurement comes with a coefficient of variation, which is bluntly spoken, there's actually quite some variation with some parameters. It's like it's definitely not true that it's perfectly measured. But again, for the sake of simplicity, let's stick with that definition. So y comes with an error, x comes with perfect accuracy. So now let's dig deeper into this. So we have yi is beta 0 plus beta 1 multiplied, okay, we talked about this, beta 1 multiplied by xi plus the residual error for each individual data point, which is the error from that predicted line, right? So it's the residual. So we have beta 0 is the intercept and beta 1 is the slope. So talked about this, we saw that set x multiplied by r becomes set y hat is transformed to y hat and becomes now intercept and slope. Assume we obtain a BIOS estimation for beta 0 and beta 1, denoted as beta 0 hat and beta 1 hat. And we will do this estimation later on. But for now, we basically will become here now an estimated function, an estimated pair of estimated entries for each individual. You're basically going back to back depression inventory and stressful life events. So we get an estimate for how many stressful life events will result in whatever depressive score. And this essentially will be then a solid function that essentially will have outliers and will have deviations from it. So here we have the predicted value, y hat I, predicted for each individual, because each individual will have a number of stressful life events, and regardless of whether it served the development of the prediction equation, it will have one predicted parameter that essentially again results in one residual. And this is the residual here, because this is the individual yi. So this is subject 3, and subject 3 had 4 life events, any number of life events, obviously, but let's say he or she had 4 life events. There will be a certain prediction, and this difference is the so-called residual. Good. What's happening? What is happening? Okay. And this again comes now to, and this is the graph that actually is one of the extra files. So the mathematical expression for a straight line is a and b. Yeah, you can use whatever letter you want. Funny detail is like, so I dealt with that. I learned that in Austria for us it was k and d. Here it's a and b. Okay, it comes to the same thing. This term that stands alone is here a is the intercept, whereas the b is the slope. So this is the change in y when x changes by 1 unit. So this is, if you remember again, back to that spreadsheet that I showed, it's like, that's our set x. So we come from x to set x, from set x multiplied by r, we come to set y hat, from set y hat we come to y hat. Y hat for 0 is our intercept, y hat with 1. We're building the difference to y hat of 0. We get the difference, that's the slope. So again, here shown. So this is our estimate, this is the model fit, and this is the slope. So the interpretation of this for our blood pressure data now is here 134, 802 plus 1.86 multiplied by x. So now this is obviously not how this relationship really looks like. So this is definitely not an in vivo example. So this would imply that with an increase of 10 milligrams per deciliter of blood glucose, you would have an increase of 19 millimeter Hg in blood pressure. That's obviously not what's happening. But again, for the sake of simplicity, let's stick with that example. And it's a simulated example. You've seen the data, right? So it's a great example because it's normally distributed data. It's nicely presented. It has comparable and real life kind of means, but the dynamic is just too strong represented. But now what is really important here in this context, the interpretation of 1.80, this is the expected change in systolic blood pressure associated with 1 unit change in serum glucose for the target population. So this is fine, right? But the interpretation of the intercept is just problematic because the intercept would imply that somebody with a blood glucose of 0 would have a blood pressure of 134.802. So bluntly spoken, there's only one blood pressure an individual of blood glucose of 0 would have, and this is essentially 0 because that individual is just plainly spoken bad. But yeah, so essentially, so you have quite concerning symptoms, like starting with like your blood pressure goes below 80, 60, it's like you have dramatic side effects. So that blood pressure is not happening. For that very reason, we're doing something which is called centralization. Centralization is basically factoring in that 0 maybe doesn't make that much sense. So we're factoring in X bar, which we know X bar is the mean. So it's the mean of X. So we're assuming that there's a mean in serum glucose predicting the blood pressure. So essentially we are not using the intercept at 0, but we're using it at the mean of serum glucose. So this being said, this term here now changes. It's not xi anymore, it's xi minus x bar. So by that, you essentially are fitting automatically that slope to the dynamic subtracted from the mean. So essentially by that, you get automatically a corresponding intercept at the mean of X. So when we do this now, realistically, we're essentially getting here fit to ln. So we're getting now a y hat of 228.73 plus 1.864. So Hongbin, Professor Seng in his lecture also pointed out that 3 decimals is maybe a little bit of an overkill. I also want to emphasize that to you, 3 decimals is like, don't put more than 3 decimals. I think 2 decimals is widely enough. And you can easily do this with the round function. So have a look at the round function. So essentially 228 is now essentially the new intercept. This is the mean of this simulated data set. It's biologically easy interpretable. It's substantially too high. So you basically 228, you're already in the diabetic arm. So usually you would assume 100 to 120 is kind of a normal blood serum glucose. Okay, but again, the interpretation of the slope remains the same. It's the change in systolic blood pressure with 1 unit deviation from the serum glucose. The interpretation of the intercept is essentially now centralized to the mean serum glucose and is not around the mean of 0 anymore. The intercept of 0. Okay, so this was this. I hope that was somewhat interesting and you found it good. I went a little longer and a little more into detail than I actually meant to go, but I think it was worthwhile to kind of look into how do you actually calculate that stuff? It's like, it kind of makes it easy. And I will also post that spreadsheet. I think it's a nice example. It's a nice calculation. Those of you who are a little bit more interested can dig deep and have a look into this. It's not essential. Essentially is what the main lab, the main lecture contains. Good. So 228.3 was now the mean. So don't confuse this with an intercept. So this is a centralized kind of serum glucose instead of an intercept, and it's a different interpretation and makes it biologically easier to digest. Good. Hope this was all reasonable. Questions, please post them to the discussion board. Guys, just have a good conversation about the topic. I encourage you. I will chime in. I'll be traveling next week, next 2 weeks actually, but I will definitely make sure to monitor the discussion board, and I really would have liked to have good conversations around the topic. And I think it makes a lot of sense because you basically, this is an online class, and this online class basically lives from you guys corresponding with me and corresponding amongst each other. And you are at a university to learn how to talk about topics. So don't hold back. Like, ask any questions. Like, you need to have these conversations to solidify your thinking. So really take advantage of the discussion board, and let's please absolutely have conversations about the topic. So I will be also posting the lab, which basically allows for the description of variables. We will look at plots between two variables, and we will fit a simple linear regression, and we will read external data where we have some registry data from France. All right, good. Talk to you soon in the lab, and talk soon. Post questions to the discussion board. Bye-bye.